Alright, silly people, here's the situation. Here we have the stationary states for the free particle and the delta function potential, so it's not really a free particle. And then also the scattering states for the delta function potential. Um, and what we need to do is we need to actually check that they are, in fact, orthogonal to each other, which just means that we're going to be multiplying them together um, and taking the integral of it and making sure that it's zero. Um, so let's just do it. We got root m alpha over h bar, and already because psi 2 um, has different constants depending on if you're in negative position or positive position, I'm just going to go ahead and split the integral up into negative and positive parts. So here's negative parts. We got minus infinity to 0 e to the m alpha x over h bar squared times a e to the I k x plus b e to the minus I k x dx plus the positive stuff, so 0 to infinity, e to the minus m alpha x over h bar squared, f e to the I k x plus g e to the minus I k x dx. Um, what I'm going to do is I'm going to split these up in fancy fashion. Not too fancy though. I just want to put them all in forms where they're easy to just crank out solutions for. Plus m alpha x. Yeah. Plus f 0 to infinity into the minus m alpha x over h bar squared plus ikx dx plus g 0 to infinity into the m minus m alpha x we over h bar squared minus ikx dx. Okay. Now, all these integrals are pretty easy. For the 0 to minus infinity ones, we keep the positive contributions, so it's a over uh, m alpha over h bar squared plus ik, and plus b over uh, well, m alpha minus ik, and that's actually m alpha minus h bar squared. No, it's not. It's m alpha over h bar squared minus ik. And we have minus f over ik minus m alpha over h bar squared minus g over minus m alpha over h bar squared minus ik. Okay. I'm going to multiply everything by a factor of h bar. Just to make it prettier. And I'm also going to fix the signs on everything. So we'll have ikh bar squared there, and then m alpha minus ikh bar squared plus f over m alpha minus ik, ikh bar squared plus g over m alpha plus ikh bar squared. And you can see that already we have things that share denominators, so let's just collect those. It's a and g buddy up, and also f and b buddy up. We're going to make it all into one fraction. Doing a little bit of cross multiplication. You remember that from Algebra 2, right? That's going to be actually plus k squared h bar fourth. And now this is a plus g times m alpha minus I k h bar squared plus f plus b m alpha plus I k h bar squared. And I'm going to group it together in a way that's a little bit more suggestive, actually. Because right now it just kind of looks like garbage. So everything's multiplied by positive m alpha. So I'm just going to say m alpha times a plus b plus f plus g. And everything is also multiplied by IKH bar squared. But then that is going to look like f minus g minus a plus b. And at this point, it's worth looking back into the chapter at the part where Griffiths decides to apply boundary conditions to these wave functions, and he finds relationships between the constants. Namely, the fact that the wave functions have to be zero at the boundaries give rise to this expression, f plus g is equal to a plus b. But then the condition that the wave function has to be continuous at the boundaries gives rise to this equation here. Right. Now, this one I'm actually going to massage a little bit just to make clear like what I'm actually doing with it. Okay. Going back to the results of our integral, we notice that we can just, and these should both be squared, but it doesn't matter that much. We have 2m alpha times a plus b, since f plus g is the same as a plus b from this. And then this says this is minus 2m alpha a plus b. So they cancel out, so it's 0. It took me way too long to figure that out.